from sand to silicon.
This is the raw material chips are made of: sand. It is made up of silicon dioxide. Silicon is the second most common element on the Earth's crust and only exists in bonded form. Complicated chemical and physical processes are needed to convert silicon into a crystalline form and make sure the crystals will meet all the requirements necessary for chip production. The final product is a monocrystalline silicon rod of highest purity. This means the rod has only one impurity atom for every 10 million silicon atoms. Silicon is a semiconductor. Its atomic structure looks like this. Each silicon atom has 4 outer electrons. There are no free charge carriers. The pure silicon monocrystal is non-conductive at room temperature. To make it conductive, small quantities of specific impurity atoms such as phosphorus are built in. Phosphorus has 5 outer electrons. The 5th phosphorus electron built into each molecule of the silicon crystal lattice can move freely. Because of this structure, the silicon phosphorus crystal is negatively charged, or N-conductive. Boron atoms, on the other hand, have only 3 outer electrons. When they are built into the silicon lattice, 1 silicon electron is missing. This creates electron holes. They move through the crystal like positively charged electricity particles. The material is positively charged or p-conductive. The transistors in modern memory chips are constructed from p and n-conductive layers such as these. Transistors are the smallest control units in the microchips.
Microchips combine a precise assembly of electronic components into one very small unit. They are built for an endless variety of specialized functions and are embedded into almost every electronic device. A microchip is protected within a case shielding connection pins going to and from the circuit board the chip is attached to. Microchips are generally used to modify analog signals or process and store digital data. Amongst all the microscopic wiring, tiny electrical switches, called transistors, are the brain of a microchip. Transistors enable the chip to make decisions and produce useful results based on some form of input. Now let's take a look inside a microprocessor, an advanced microchip at the heart of every computer system. This type of microchip performs a logical or mathematical operation on incoming data based on instructions from software. Digital text, sound, and graphics are all represented as a highly complex collective of only 2 electrical states, represented as 1 or 0. Called bits, these are the simplest elements of data computers work with. Incoming bits travel along a data bus, and within the processing core are operated on not by millions, but by billions of transistors. The constant switching of these transistors is interpreted into useful information. The results get passed to the integrated memory controller, which directs traffic to and from the processor. The entire cycle completes in under 1/1000th of a second. Now the processor is ready to work with the next set of data. Microchips form an indispensable element of our everyday lives, and each year they are being built faster, smaller, and more energy efficient. We welcome you in taking a look at the incredible world of microchips.
Over the past 20 years, electronics has gone well beyond computers. We are living in an e-world. Everywhere we can see the application of electronics and various electronic gadgets. From the moment we wake up in the morning, till we go to bed, and even while sleeping, we use electronic devices. Electronics, nowadays, is not about a computer or a calculator, but it plays a major role in almost all areas of our lives, from an LED to a completely automated rocket launching station.
In the simple things that everyone understands, everyone I think relates to electronics being in computers, and everyone relates to electronics perhaps being involved in telecommunications. But over the last 20 years, electronics has really kind of been pervasive in everything, every facet of our lives. To more simple things like your washing machines and other household appliances that have a tremendous amount of electronics in them.
Let's look into a car. Your car has so much electronics in it. But you might not have noticed. The modern safety and security measures, like airbags, ABS, and even the engine, use some kind of electronic control units. The starter motor, indicators, wipers, power windows, car stereos, locking system, air conditioner and the speedometer make use of electronic components and technologies. Anti-lock braking system. Let's take a closer look at how they work.
When the driver fully applies the brakes in a vehicle without the anti-lock brake system, the brakes can lock. This causes the wheels to stop turning, which makes the tires skid. Skidding tires have very little grip and are not effective at stopping or turning the vehicle, so the driver may be unable to take evasive action. With ABS, when the driver fully applies the brakes, the system uses sensors to detect any brake lockup and rapidly pulses that brake to prevent it from locking. This helps to prevent skidding so the tires can maintain grip. It also helps to allow the vehicle to be steered around obstacles while braking.
Airbags. The first stage of the airbag deployment is the accident itself. The collision activates an array of sensors in the vehicle, including accelerometers, impact sensors, side pressure sensors, brake pressure sensors, gyroscopes and seat occupancy sensors. All these sensors are in intimate connection with the ACU, Airbag Control Unit, the very brain of the airbag system. The unit decides if and how to deploy the airbags. When the ACU detects that the deployment threshold has been reached, it initiates the inflation stage. Only a very few applications of electronics are pointed out here. Electronics and communications has grown and gone beyond the limits of the sky, and is still flying to conquer more and more.